Electromagnetic radiation. Now, every particle in the universe has some sort of movement and emits a radiation. And this includes the cells in your body to the sun. And this is electromagnetic radiation. And what it is it's a magnetic field, waves of a magnetic field that propagate through space carrying radiant energy. And as I said before, everything in the universe emits EM, except when you're at 0 Kelvin, that's when atoms cease to move, and you will get no vibrations, and that's something you'll never experience. That's almost impossible to get to 0 Kelvin. So the EM spectrum, it is a wide range of frequencies from low frequency DC all the way up to super high gamma rays. And some examples of that frequency is the visual spectrum that we can see every day, which happens between 480 terahertz and 790 terahertz. If you remember the old style of TV broadcasting, that took place between 54 megahertz and 806 megahertz. But the frequency band that we're most interested in is the RF band, or the radio frequency band. This takes place between 20 kilohertz to around 300 gigahertz. And this is important because our wireless communication, it occurs between 2.4 gigahertz and 6 gigahertz, which is part of that RF spectrum. And also you can combine in 60 gigahertz, as we know that's now coming into the wireless world as well. So now that you have an understanding of basically where we are in that radio spectrum, we're going to talk about waves and the basic radio wave characteristics. So the wave is the most fundamental component for RF communication. It is a repeating function over time. And one of those cycles within that wave is called a wavelength. And that is important because that is that basically tells you how your wave will interact with physical space. On top of that, you have the amplitude, which is the amount of energy or signal strength that you have in your wave. Now, some simple wave calculations. Lambda, that's your wavelength measured in meters. You have your frequency in hertz. And you have c, which is your speed of light, which is close to 300 million meters per second. And this is a constant value. So the way you would find out your wavelength would be c over f. Or you could find your frequency by going c over the wavelength. Now, the frequency is inversely proportional to the size of the wavelength. So essentially what we're saying, the larger the frequency, the smaller the wavelength. And this is all important, as a high frequency wave would be impacted by something like a droplet of water. If a frequency goes through and it hits that water would have a significant cross section, and that wave would be bounced by the water droplet. Okay, polarization. This is the next part of the wave fundamentals. So polarization is the horizontal or vertical orientation of a wave. So in nature, if you could actually see one of these electromagnetic waves, not only would you see a wave traveling up and down, but you might see a wave traveling side to side, diagonally. You'd see waves in not just one plane. And this is very important for two reasons: antenna theory and understanding how to receive the maximum RSI, or received signal strength. Now, to give an example, a practical example, think of yourself as you're painting a flagpole, and you and your paintbrush is the transmitting antenna, your paint is the signal, and the flagpole is the receiving antenna. Now, if you were to paint that flagpole, how would you be able to transfer the maximum amount of paint to it? If you tried painting side to side, you wouldn't be getting much paint on, but if you did it up and down strokes, you'd be able to transfer a lot more paint to the flagpole. The same principle applies to the antenna. If your antenna is polarized on the horizontal plane and sending a signal to the vertical plane, you're not going to be transferring as much energy. Now, both your transmitting and receiving antenna are in the same polarization. They're both vertical, you'd be able to transfer maximum amount of energy. So that's one thing to keep in mind. Material interaction. So now that we understand the wave properties, we're going to discuss how waves behave when interacting with different types of material. So all material will bounce energy. It's very hard to dissipate energy into a material unless you're driving a current through that material. Now, the reason why is that all materials have a certain dielectric constant and impedance, and that affects the way that the speed of light can move through that material. So, for example, if you have a drywall, there isn't that much of a, there's a higher dielectric constant than air would, and the impedance is much, so maybe half the signal would go through the drywall and half would be reflected back. However, if you look at something like water, you would, water acts like a metal almost, so almost all your signal you put into the water, gets reflected back. Only a tiny portion will go through. So that is the basis between, behind material reflection. And just a common list of reflection of common materials. As you can see, air. So when we talk about air, we're talking about free space air, just the regular air you'd be transmitting signals through. That we say has a dielectric constant 1 and a reflection of negative infinity, which means that it doesn't reflect at all. You go down to something like snow, it's still very low dielectric constant, but you can still get reflections, and that's why at night you can see snowflakes. And then you go all the way down, you see something like water, which has a higher dielectric constant of 81 and a reflection of negative 1.9. So the bottom line is, the larger the dielectric constant, the larger the reflections you'll get. So now that we understand how the waves work and the type of material works, we're going to talk about how waves will propagate through the air and the power that it is carried through the air. So we're going to start off with RF power. So RF power is linearly represented as milliwatts and logarithmically represented as dBm. Now dBm is it stands for decibels relative to 1 milliwatt. So 0 dBm is not 0 power. A 0 dBm is relative to 1 milliwatt. So 0 equals 1 milliwatt. Sounds a bit complicated, but that's how it is. And the way that we convert watt to dBm and back is by using these logarithmic functions you see on your screen. So engineers, we're kind of lazy, so we figured out an easier way to do it using the old slide ruler technique of the 60s. We came up with the 3 and 10s rule. So for every doubling of power, we add 3 dB. For every halving of power, we subtract 3 dB. And for every time we increase the power by tenfold, we add 10 dB. And if we decrease the power by tenfold, then we subtract 10 dB. So here are some examples. So a 3 dB point, that is a double of power. So 0 dB plus 3 dB, that's the same thing as 1 milliwatt times 2 milliwatt, and you get 2 milliwatts as your answer. And to go backwards, 10 milliwatts, what is that in dB? Well, that's a 10-time increase from 1 milliwatt. So we know that 1 milliwatt is, so 10 milliwatts equals 1 milliwatts times 10, or 0 dB plus 10 dB, which would be 10 dBm. And you can do the same thing for 40 milliwatts. You can figure that out. We know that's 1 milliwatt times 10 times 2 times 2, and then which would come out to 16 dB. And then same thing, even with negative 46 dB, that comes out to 25 nanowatts. That's a big mathematical calculations. So now that we understand power, we can talk about propagation. So propagation is an important concept in RF communications. This is essentially referring to as the signal attenuates as it travels through a medium. And because antennas are mostly going to be in airwaves, we're not really expecting to go through materials as much. So we're going to focus on free space propagation, which is the propagation of a signal that radiates from an antenna and goes out into the air. Now, we can calculate what happens in the first meter by this mathematical formula, but all you need to really remember that's important is 2.4 gigahertz means that there'll be a loss of negative 40 dB in the first meter. And at 5.86 gigahertz, we know that there's a loss of around negative 48 dB in the first meter. Those are two most important facts you need to know. However, the world of physics can be very funny at times, and mathematically, after the first meters, things change. So now, after the first meter, every additional distance with a factor of 2 results in a 6 dB loss. So 2 meters, you would have 2 meters after the first meter, you would have a 6 dB loss. 8 meters after the first meter, you would have 18 dB of loss. And distance of 10 result in a 20 dB loss. So after the first meter, 10 meters would be 20 dB loss, or 40 meters would be 60 dB loss. So let's work through a small, simple mathematical example. What would be the RF attenuation that, as a RF signal, travels through 801 meters through free space? So that's simple. We know 800 meters is 1 meters times 10 times 10 times 2 times 2 times 2, which is 2 distances of 10 and 3 distances of 2. So from our formulas above, we know that 800 meters would equal to 2 times 20 dB plus 3 times 6 dB. So that equals to 58 dB of loss. So now at 2.4 gigahertz, we know that at the first meter, we have that negative 40 dB of loss minus that 58 dB of loss to come out to 98 dB of loss. And we do a similar calculations at 5.86 gigahertz, where we come up with negative 106 decibels. So now that we know about signals, how they go through space, how they go through different materials, we can put some application behind it, and we will talk about antennas. So we're going to talk about the antenna physics. The basic antenna is a piece of wire with electrons flowing through it. As you can see from the animation, what is happening is as electrons move up and down the wire, it creates an electromagnetic field that emits omnidirectionally. So that energy just propagates like completely outwards in a circular pattern. And as I mentioned before, this is known as an omnidirectional antenna. Now, if you add 2 antennas, or as we call them, 2 elements, we get a difference in the shape that we're receiving. So as you can see in the animation, this is no longer a nice circular pattern. Now what has happened is we have 2 antennas, they're the exact same gain, they're the exact same phase, they're just half a wavelength apart from each other. These 2 antennas, they end up canceling the side antennas. And you're with this shape that just propagates signal forwards and backwards with nothing on the side. So this is your simple antenna array. And we can manipulate this arrays even further. By introducing additional antenna elements, we can see that, like for example, this will have now 4 elements, and you can see through the animation how the signal changes. So these are 4 elements, all the same gain, all distance the same half wavelength apart, all in phase, and we can see that this is a much larger gain signal. It's a very narrow beam, and we can also see side lobes that are developing. So this is happening because 4 antennas, they're all shooting out signals, and they're all mathematically adding and subtracting each other and causing this effect. So this is the beginning of complex antenna design. And we can also shape the way we want our signals. So the first way we're going to do it is through something called amplitude shaping. So taking our last image that we had, now what we're going to do is the exact same setup. We have 4 elements in phase, all the same distance apart, but now instead of all being at the same gain, we're going to increase the 2 center antennas by a factor of 3. And now you can see what happens is, you can see that the antenna has actually gotten rid of all those side lobes, and you can see through the animation, it's a much cleaner signal. However, if you remember from the last slide, this is now a much wider beam. So again, this is to do with antenna calculations and subtraction. So it got rid of those side lobes, but also added additional focus power in the up and down direction. And the final shaping we can do is something called phase shifting. So now in this example, we've kept all the elements the exact same gain. They're exactly the same distance, half wavelength apart. However, there's a difference in the phase. So there's a time delay between those antennas. And through that mathematical addition and subtraction, we're actually seeing that we're bending the wave. We're actually bending and tilting the main beam to a different direction. And we're also introducing a bunch of other side lobes and other types of signals. So through modifying the phase, you can get that tilt. And this is the fundamental formation, or the fundamental basis of beamforming technology, which we'll cover in the advanced Wi-Fi course. Now, one thing I want to discuss is antenna patterns. If you remember seeing those antennas and the shapes they were going, you might be confused, and I think it's sort of worth mentioning to explaining what those antenna patterns means, which will help you understand how your antennas work. So, to your right, you would see two patterns. You see two circles, both with shapes. Now, these are antenna patterns. There's a horizontal and a vertical. Now, these antenna patterns, they describe the antenna's variation of power with angle. There's no distance information at all. There is a 3dB point in most of these antennas, and that basically tells where most of the energy resides, and it also determines the shape of the antenna, or the angle of the antenna as we call it. So the first antenna on the top, the azimuth antenna, this represents the horizontal propagation of the beam. So yes, it's horizontal, but the way you would have to imagine it is, imagine you're looking at the antenna from the top, from looking down on the antenna. How it propagates horizontally, that's what you would see. This is an omnidirectional antenna, so this is a uniform pattern. We don't have a 3dB point here. We just know how far where the maximal energy would be. The second antenna on the bottom is the elevation or vertical antenna, and that represents the vertical propagation of the signal through that antenna. Now that is a lot more different than the azimuth horizontal antenna above. And again, you'd have to look at this and imagine you're looking at this from the side of the antenna. And if you're walking around this antenna from a 360 degrees of view, it would have this exact same pattern. All right. These 3dB points, they reside between 75, 105, and 255, and 285. So these are the areas where most of the energy resides. And this also happens to be the 30 degrees. So 75 degrees to 105 degrees is 30 degrees. And so this would be considered a 30-degree plot. And you can also see the side lobes that are available. So you know that if you walk around from the antenna, you know that the energy would spread out in a 30 degrees pattern. But when you look at it from the top, see how the horizontal propagation, you can see it just spreads out evenly. So maybe if I explain how a sector antenna works, this will make more sense. So if we look at the horizontal, you can see that this is much different. The energy isn't radiating in a uniform pattern. This is all pushing the energy out in one specific area. Our 3dB points are between 135 and negative 135, and on our map, you can see that maps out to a 90 degrees pattern. So from a horizontal, we can tell this is a 90 degrees antenna. And there's very little or hardly any energy that's going behind this antenna. On the vertical, we can also calculate a negative 165 to a 165 pattern, which comes out to about 30 degrees. So we can tell out from a vertical perspective that this is emitting energy in a 30 degrees patterns. And you can see side lobes and back lobes that are also visible. And on the bottom left, you see a 3D rendering. So hopefully that makes more sense on what is actually going on. But that's how you would imagine that the signal would be pushed out. Now, I did mention in the first antenna pattern slide that we don't talk about distances, and that's still true. We don't talk about distances. But however, we can use distances to help us understand coverage at certain areas if we know what for instance, what the height of the antenna would be. So if we were to say mount an antenna at a 20-meter height, using simple trigonometry, actually simple high school math, and we were able to find out what that angle of a user would be receiving signals at. So we'll say the AP is at a 20-meter height and a user is 20 meters away. we were able to calculate an angle of 45 degrees. And even if the user was 50 meters away, we would be able to calculate that angle at 21 degrees away. So we would understand exactly how to do a plot. One thing I want to bring up is we did mention earlier on that most of the energy is focused at the negative 3 dB points. And so one question that someone would come up with was, hey, I'm at the 20 meters, I'm not in that 3 dB point, am I going to get any energy? And the answer is yes. Maximum energy is going at a 3 dB point, but still, you can see energy is still radiating out. And if you even remember that a few slides back when I talked about the distancing for every factoring of 10, you have to add 20 dB. You can still see that at 200 meters out, you would still get, it would be a lower signal, but it would probably be in a similar range of what you would get at 20 dB, even though the antenna pattern shows a lower signal. All right, so now we're just going to go over some of these sector antennas again, and just to give you a better idea. Now, another customer issue that we've heard in the past is, you know what, I need a lot of coverage, so 90 degree antenna won't work. I need 135, 150 degree coverage antenna. And our answer is no, you don't. And this is really why. That 3 dB point that we're talking about earlier on, I said before, that's not where the energy stops off. Now, if we were to look at a heat map of this antenna, sure, we can see that if you look at the 90 degrees angle, you would be able to see, okay, there's a lot of signal strength right there, but you can also see outside of that 90 degree angle, there's still signal happening. So you're still going to be fine with that. So this kind of 90 degree angle, this is great for broad coverage. That spectrum is just spreading out, and you'd have a lot of energy. And you can go up by 10 meters. So basically, the first square on the left, that's the antenna at a 5 meter height, then a 10 meter height, then a 20 meter height. Now, we can even say, hey, what if I want to throw in a down tilt? So this is an antenna at a 10 meter height with a down tilt. 0, this is what we saw in our last slide, but at a 15 degree tilt, or at a 30 degree tilt, you can see that the down range isn't changing, but we see a widening of the signal when you add more tilt to it. All right, so a 60 degree antenna. This is not as wide as a 90 degree antenna, but still same concept. This signal is a lot more narrow. There's more signal happening downrange. This kind of antenna is used more for targeted coverage. So you can see the differences at 5, 10, and 20 meter installation heights. And mind you, a lot of this will be covered in the outdoor AP class as well. So please take that if you're interested in this. Now, a 30 degree sectoral antenna. So this is a very, very narrow bandwidth. And if you can see that beam and a heat map, you can see how that signal changes quite a bit. You have that 5 meter, 10 meter, and 20 meter. So height, you can see definitely how the closer you are to the ground, the more that signal is spread out. The higher you are, you can see a bit of null zones here and there. So this is not a great antenna for broad coverage, but it's great for point to point. And it's even better for top-down coverage. So instead of pointing and shooting that antenna out, if you were to shoot that antenna down, you would end up with these nice footprints. There is not much spillage taking outside. So look at the 10 meter installation height, that's a really nice signal. And if you even go to 20 meter heights, that's still a nice signal. Everything is contained within that access point. You're not getting many side lobes. And those lobes you are getting in there, their signal strength is very, very small. So this is great if you want a wide, fatter pattern. This is the kind of antennas that we use on a stadium or convention centers to give us the best maximum coverage.